Welcome to the office. We want to take a look at evaluating integrals today, where we have to decide which method that we're going to use. So let's take a look at an example here. So for this particular example, let's see, we have polynomial divided by polynomial. And if we ask ourselves to follow through, a particular strategy that we've been considering, we might try to first simplify this expression if we can, and there's not much to do. This quadratic is not factorable with nice integer coefficients, so it's certainly not going to cancel out with the x plus 1. So we say, okay, well, it doesn't really simplify. Okay, so are there any obvious substitutions? And one thing that I would certainly encourage you to watch for when you have polynomial divided by polynomial is to see if something in the denominator is the derivative. When you take the derivative, you get the numerator. So the derivative of a quadratic is a linear, so this looks promising, but the derivative of x squared gives us 2x, so that doesn't match. And the derivative of 4x is 4, so that doesn't match. And of course, derivative of a constant is 0. So I'm not looking at the overall fourth degree polynomial that I have in the denominator. Rather, I'm just looking at the quadratic that's being squared, because if I can let u be that quadratic, then I would have potentially 1 over u squared. And that could look very nice. So I don't necessarily have that as an obvious substitution. There's some manipulations that we could make to kind of start to force that situation. So let's see if there's anything that would look a little bit nicer for us. So we move on and we say, let's try to classify the integral. If it's trig functions, nope, not trig functions. So it's not going to be integrals of powers of sine or cosine, tangent or secant. Rational function, yes, it is. It is a rational function. Again, it encourages actually partial fractions in this case. So partial fractions, would that be a good idea? Well, if you think about that, partial fractions, what this would lead to, I'm going to write this in maybe black here so we can recognize that I'm going to end up erasing this. But if I wanted to find the x plus 1 divided by x squared plus 4x plus 8 squared is equal to ax plus b. Since it's a repeated quadratic, irreducible quadratic, we would need a factor of a fraction of with denominator x squared plus 4x plus 8, and we would need a fraction cx plus b in the numerator with x squared plus 4x plus 8 squared in the denominator. So if this is what we're looking at, right, we're looking to write this in this form, I would say it's pretty clear that, well, c equals 1 and d equals 1, right? And that's exactly what we have over here. 1x squared plus 1, sorry, 1x plus 1, 1x plus 1 over this thing squared. So this is just 0 and this is 0. If that's not obvious, I would encourage you to go ahead and work through this example, right? Work through finding what the coefficient should be if we were to use partial fractions. You will find that a and b are 0, and that there is, right, the partial fraction doesn't go anywhere. It just gives you the exact same integral. So it doesn't give you anything at all. So we say, partial fractions isn't going to work, even though it's a rational function. So we move on. Integration by parts. Is it a product of a polynomial and transcendental? No. Okay. Are there any radicals? No. So we're not going to do, it doesn't encourage a trigonometric substitution. But if we look carefully, we will end up seeing that there is a trig substitution to do, but it's not obvious right now. So the best thing that I've been able to identify so far, looking at the first recommended steps, is to, right, that obvious substitution isn't there. But if I kind of skip forward into our last method where we try again, right, we manipulate the integrand. This is really something that should be pretty approachable even as a first step. What we're going to do is we're going to manipulate this integrand so that way it fits into a nice substitution. It's going to give us one nice substitution, but then we end up with something else that we still have to work with a little bit. But I figure this is the best way to go about it. All right. Several steps to this example. So please follow along carefully. All right, what I want to do is I want to make the numerator look like the derivative of x squared plus 4x plus 8. So I need two x's instead of just one. Now, rather than adding an extra x and subtracting it, because that's not going to provide me the most benefit long run, what I'm going to do is I'm going to actually just multiply the numerator by 2 to give me 2x plus 2 in the numerator. But if I multiply by 2 in the numerator, I also have to divide by 2 in the numerator, which means I'm just multiplying the overall integral by 1/2. So that doesn't quite get me what I'm looking for yet, because I need I need that plus 4, not plus 2. So I do a little bit more work here. What I'm going to do is I'm going to go ahead and I'm going to add 2, another 2 in the numerator. So I have 1/2 times the integral of 2x plus 4 by adding 2. And then I'm going to subtract 2, so it's overall the same. And I have x squared plus 4x plus 8. Remember, what we're doing here is we're trying to make the numerator look like the derivative of the denominator, or this quadratic. And so we're looking to have 2x plus 4. And I have that 2x plus 4. I just have this extra minus 2. So I'm going to split the integral up. So I've got 1/2 times the integral of 2x plus 4 divided by x squared plus 4x plus 8 being squared dx. And that looks fantastic because now the numerator is the derivative of this quadratic. But I have this minus 2 in the numerator. So I'm splitting this up as minus, right, this is 1/2 of the integral. So when I split the integral up, that 1/2 has to be there too. 1/2 of 2 divided by x squared plus 4x plus 8 being squared, right? Because I can take this one fraction and split it into 2 by separating the numerator. That's not a problem. Of course, the 1/2 and the 2 will reduce, so the 1/2 times 2 is just 1. So there's just a 1 here in the numerator. Now, this is where we have to be very careful about presenting our work. We have 2 integrals to evaluate. This integral is rather straightforward because we created a numerator that is the derivative of this thing. So we can perform a very nice u substitution and end up with 1 over u squared du. This one is not quite so nice. If we didn't have this square here, of course, it would be very nice as well, but we do have this square there. In particular, if we didn't have the square, we could use our formula sheet to help us, right? Depending on which formula sheet you have, you might notice that you've got, let's see here, if I can grab this for us a moment. We've got a nice formula for the integral of 1 over a squared plus u squared. And why does that seem beneficial? Well, anytime we have a quadratic, we can complete the square. So we can always write a quadratic as something squared plus something. Sometimes we have the unfortunate situation of it's already a perfect square, right? A perfect square of a linear factor. That's interesting, but that's not the case here. It doesn't fit this idea anyway, simply because we have this denominator being squared. So the square kind of ruins that for us. So we've got to keep thinking. So we've split this into 2 integrals, where one of them has that nice obvious substitution, and the other one we still have to work with. But this new one is a little bit easier to work with because this one would in fact encourage a trigonometric substitution. This is kind of similar to something that we saw in the past, right? Relate things that we see now to things that we've seen in the past. We saw something very similar to this earlier in our discussion on trigonometric substitution. So hopefully you're remembering that. If not, feel free to take a look at the previous examples that we considered. Those examples are useful, of course. All right, so how do we present our work? Well, this is a difficulty. If you wanted to evaluate both of these integrals in line, this one is much easier to evaluate. This one takes quite a bit of space. So what I might encourage you to do is to kind of evaluate them separately. How you present your work exactly is up to you, but in my initial work, I found that it was a little bit difficult to have such a nice, clean work by holding them both together. So what I'm going to do is I'm going to say that 1/2 of the integral of 2x plus 4 divided by x squared plus 4x plus 8 being squared dx, I can evaluate this using the nice u substitution. So u is equal to x squared plus 4x plus 8. And that would give us that du is equal to 2x plus 4 dx, which is exactly what we have, right? Numerator times dx. So from there, we are able to perform our substitution. Numerator times dx just gives us du, and the denominator is u squared. This, of course, should be pretty straightforward. We should recognize this as a u to the negative second power. So we have 1/2 times, increase the power by 1, so -2 raised to a -1, and divide by the new exponent. So 1 divided by -1 is just multiplying by negative, right? That's the same. We could include the plus c here, but we're going to have to bring everything back together anyway. So we don't have to include the plus c, but if you wanted to, there it is. Don't forget to substitute back. -1/2 x squared plus 4x plus 8 to the negative first power. That gives us the evaluation of this first piece of that. So we have that. We'll bring that together with what we find for the second integral to give us the overall value of the integral. So the other piece I'm working with now, we'll call it 1/2. We just don't want to forget to perform the subtraction. 1/2. Oh, sorry, the 1/2 and the 2 canceled out. So there's no 1/2. It's 1 over x squared plus 4x plus 8 being squared. The thing to make note of here is that we can always complete the square on a quadratic. And when we complete the square, the details of this I'm going to leave for you to fill in, because I don't want to spend forever working on this problem. So I'll leave it to you to observe that we can complete the square as x plus 2 being squared plus here, this other thing we have, right? We complete the square to find the x plus 2. Finding that is the action of completing the square. What we're left with happens to be 2 squared. So now we have variable squared plus number squared. When we have that situation, this may encourage us to look for a trigonometric substitution, or again, if, sorry, we're missing something here, squared. I don't want to forget that. That's a very important detail to this problem. Yeah, let's go ahead and make some room there. Squared. Without this, we could just use this formula here, and that would be very nice. But we don't have that. We have the square, right? We don't have the lack of square, we have the square. So we say to ourselves, what method do I take? Well, in the past, I had encouraged us to view something like this as the square root of this being raised to the 4th power. So that way the square root and the 4th power reduced to just a square. That would allow us to recognize the use of trigonometric substitution. So what trig substitution do we want to use here? Well, again, feel free to review our content on trigonometric substitutions to recognize that the substitution we want here would be x plus 2 is equal to 2 times the tangent of theta. Now let's see here. I want to give a little bit more room here, maybe, just to clarify. We're doing a trig substitution. X plus 2 is equal to that. When we differentiate here, we get just 1, of course. So this is dx is equal to, differentiate here, we get 2 secant squared theta d theta. And this allows us to perform our trig substitution. So the integral is equal to the integral of 1 over the x plus 2 squared is going to become, let's see, I want 2 times the tangent of theta being squared plus 2 squared, right? X plus 2 is 2 tangent theta. That's still being squared. And it's not just dx, it's secant squared, 2 times secant squared theta d theta. Now, why do we use a trig substitution? Because this expression here simplifies, right? This simplifies quite nicely. 2 times tangent theta squared plus 2 squared is going to be 2 squared secant squared theta. This thing becomes that. So let me write out the integral here. 1 over. Again, this is a simplification of trigonometric functions. Tangent squared plus 1 is secant squared. We use that to recognize squared plus 1. Yeah, okay. Yep. I think that makes sense. Yeah, tangent squared plus 1 is equal to secant squared. Sorry, just double checking these things in my head. But of course, we have a multiple of 2 squared there out in front of it. So we end up with 2 squared secant squared theta. But this whole thing is being raised to the 4th power. Sorry, that's being raised to the 2nd power, which is going to make these things raised to the 4th power. And we have 2 secant squared theta d theta. All right. So where are we at now? Well, we need to do some simplification, right? We've performed our substitution. We simplify, right? We're returning back to these same steps that we do every time we're trying to evaluate an integral. We have something new now. How do we evaluate it? Simplify, check for substitutions. It's a trig, so we use trig methods. Okay, so distributing here, this is going to give us 2 to the 4th power. But 2 to the 4th will cancel out with this 2, so we have just 2 cubed, which is 8. Secant squared squared is secant to the 4th. This cancels out with 2 of those secants, so it's just secant squared theta d theta. Now what I'm going to do is I'm going to rely on a little bit of background work that we've done. We've already performed this integral in a previous example. So what I want to say to us, just to save, again, a little bit of time, using, actually here, let me write this up a little bit further. Using that secant theta is equal to 1 over cosine theta, this integral becomes 1/8 times cosine squared. And the integral of cosine squared is what we then found. But how did we find that? We use the fact that cosine squared theta is equal to 1 plus cosine 2 theta divided by 2. So we need to use that to evaluate this integral. And are we going to provide all those details? You know what? Maybe we could. Let's go ahead and give it a try. So I'm going to bring this work down over here so we can work across, and then we should have enough room. So this is equal to 1/8 times the integral of cosine squared theta, because secant is 1 over cosine. So division by a fraction multiplied by the reciprocal. Pull the 1/8 out, multiply by 1 over 1 times cosine squared theta. So it's just cosine squared theta. From here, we are able to use the substitution. So I'm going to see this as 1/8 times the integral of 1 plus cosine of 2 theta divided by 2 d theta. Now the 1/2 can be pulled out. So I've got 1/16 here. And then I'm left with the integral of 1. which is just theta. And I am left with the integral of cosine 2 theta, which would be 1/2 times the sine of 2 theta. And of course, if we wanted to include the c there, we would have a plus c. All right. That looks good. That gives us the evaluation of the two separate pieces of the sum. So we evaluated this piece and we evaluated this piece. Mostly, we didn't quite, right? We still have actually one thing to do. We did a trig substitution. So we need to recognize how that plays out for this value and this value, which is a little bit interesting. We have to use some more trig identities. So first of all, we have a triangle, and here is theta. Our substitution was that x plus 2 is equal to 2 times the tangent of theta. So if I were to use that, x plus 2 is equal to 2 times the tangent of theta. So x plus 2 divided by 2 is equal to the tangent of theta, telling us the length of the opposite side, opposite over adjacent. And this is the square root of x plus 2. Let me try to write that a little bit smaller. Square root of x plus 2 squared plus 2 squared. So that gives us the side lengths of the triangle. That also gives us the ability to find theta. But one manipulation we need to do before we can make all substitutions is to observe how we can see this as a trigonometric function of just theta instead of 2 theta. So on our formulas, we have this really nice double angle formula situation. Sine of 2 something is 2 sine u cosine u. So this is theta plus 2 times sine u cosine u. So 2 times the sine theta cosine theta, but the 2 and 1/2 cancel. So we're left with sine theta cosine theta. All right. So now I can use my triangle to help find theta, sine theta, and cosine theta. So this is 1/16 times theta can be found simply by the arctangent of x plus 2 divided by 2. Sine theta is opposite over hypotenuse, and cosine theta is adjacent over hypotenuse. So what we actually end up with there is both of them are being divided by this thing, which actually gives us the square root being squared, and the square root goes away. Right, because I have this in both denominators. When I'm multiplying fractions, they multiply across. So the square root and the square go away. No, erased too much. All right. So we'll just leave it like that for now. And then the numerators multiply across as well. And that would be x plus 2 times 2. So there, now it's written back in terms of x. That's much better, much better. So we return back to our two integrals. We evaluated this one, we evaluated this one, and we will go ahead and say what these are equal to. So overall, our integral is equal to, and maybe just to be clear here, the integral of x plus 1 divided by x squared plus 4x plus 8 squared dx. We've performed this integral. So to help us understand what we're writing down, since I'm skipping a whole bunch of stuff here, right? I did a bunch of work. Just to clarify, our final answer, the integral of this is equal to, we did this guy, so negative 1/2 of that to the negative first. So I can call it negative 1 over 2 times x squared plus 4x plus 8. And then I have plus this thing right here, plus 1/16 times the arctangent or tangent to the negative first, right? That's the same thing there because to the negative first is saying the inverse. Arctangent of x plus 2/2 plus 2 times x plus 2 divided by the square, and the square root go away to leave us with, and this is actually exactly right. This is the x squared plus 4x plus, and that's it, right? The squares go away. So could you do more to simplify that? Yeah, you could. You definitely could. One thing that you want to keep in mind there is that you can do more simplification because we have common denominators. Yeah, this looks good. So we could do some more simplification. I'll leave that for you guys to do. Let's call it good. All right, so there's a lot going on in that example. Let's quickly try to review that just a little bit. Oh, I had more room to the right. Anyway, we have an integral that we weren't sure about. Our best guess was to rewrite, so that way the numerator was the derivative of the denominator, or a piece of the denominator. That gives us the 1/u squared du. However, to manipulate it, we ended up with this extra piece, right? This extra piece over here. And this one, we should be able to recognize that gives us a trig substitution. Are there different ways that you could have approached this problem? Likely, very likely. So it's even possible that there's a much simpler way. This is just the way that I found it works. So if you have any questions, of course, let me know. Thank you for your time and your attention. I'll see you guys back in the office for another example on evaluating integrals. Have a great day.